Good morning. Excuse me. Um, Here's a video on section 4.1.3, or our third section of chapter 4, on finding multiple solutions of systems of equations. So we have talked in the past about finding points of intersection for two equations, and that's exactly what we're doing here. It's going to be a little bit more pronounced with the type of work we're going to do with systems of equations. And again, a system is just when you have two or more equations that should have some points in common. We'll talk about how to do these algebraically as well as graphically. So let's look at the first question. So solve each system below without graphing, and for each one explain what the solution or lack thereof tells you about the graph of the system. So I'm going to do these algebraically, and then put these into Desmos or the graphic calculator, so you can see how the solution would look. Now, right off the bat, I know that the answer for A is no solution, but let's actually go through the process. So, excuse me, a little congested this morning. Here you got two lines, right? Negative 3x plus 5, negative 3x minus 1. So we could do substitution. That's usually a good technique when you're solving a system of equations algebraically. So you set each one equal to each other. You could add 3x to both sides, and you're stuck with this. That's clearly not a true statement. 5 does not equal negative 1. We know that. When that happens, we could say no solution. But what does that mean graphically? Well, these are two lines, right? Both of the same slope, but different y-intercept. So negative 3x plus 5 looks like this. Negative 3x minus 1 looks like this. And those don't touch. So that's another reason why you'd say no solution, because there are no points of intersection. They have nothing in common. So the graph confirms the algebraic solution. So it's kind of better to sometimes see it graphically, because then you would make sense of the algebraic solution. Sometimes people memorize like, well, I guess if the two numbers don't equal each other, all the variables cancel. I'm just going to say no solution, but you don't really understand why. The reason why is because the graphical solution, right? The graphical solution shows that, hey, these are two lines that never touch. They have nothing in common. So of course, algebraically, we won't see an answer. So the graphical solution confirms the algebraic solution. So let me write that down. The graphical solution confirms the algebraic solution. Sadly, a lot of algebra classes don't do the graphical solution, which I think is very unfortunate, because you really need to see that to understand the algebraic solution. And we can, again, we can go to Desmos or graphic calculator and type this up. Y equals negative 3x plus 5. There's the line. Y equals negative 3x minus 1. Doesn't align. They never touch. So if I clear my screen, you see that for yourself. Or if you go to the graphic calculator and type that in, negative 3x plus 5, negative 3x minus 1. We'll graph in the center window. So you see two pair of lines. Even if you try doing the intersect feature, second trace, option 5, hit enter 3 times, you can get an error because there's no answer. It says no sign change. That's part of the algorithm the calculator uses to see where they touch. Not quite sure what algorithm it's using to do that, but calculator will give an error because they don't touch. So hopefully that makes sense for that one. Now, we'll continue the same process substitution for the other problems. Like for example, part B, y is already isolated. So it's naturally you want to just set them equal to each other. Half x squared plus 1, 2x minus 1. Move all terms to one side. That might make things easier for ourselves. So I moved everything from the right to the left by subtracting 2x and adding 1. I'll multiply both sides by 2 to avoid fractions. So I get x squared minus 4x plus 4. Hopefully you recognize that's x minus 2 times x minus 2, or x minus 2 squared. So x just equals 2. So there's just one solution just one solution. And if you were to graph it, the first one's a parabola that has a vertical shift of 1 up and a vertical stretch of 1/2. 2x minus 1 is somewhere over here with a pretty steep slope. And it's supposed to touch at 2, which will be 2 comma 3, I think. So the graph will kind of look like this. It's just going to graze the graph. Sorry, the line's just going to graze the parabola at x equals 2. That's how it will touch. How you know without a calculator could be kind of tough to do. So I think that's where the technology would help to be able to see that. I mean, again, I kind of sketched the parabola knowing this vertical shift of 1 and opening up. The line, I know I can draw that accurately. That's the slope of 2 with a y-intercept of -1. But how do you know they just barely touch? That's a little tricky. So that's where, again, a calculator can help, or something like Desmos. So if I typed in y equals 0.5 x squared plus 1, and y equals 2x minus 1, yeah, you see it just grazes it, right, at 2 comma 3. So again, the graph will confirm the algebraic solution. You see it just touches once at x equals 2. And the y value, of course, is when you plug 2 back in each equation, you do get 3 for the y value. So again, you have to make sure that they share the same y value, because they have to have points in common, right? So you need points in common for there to be a solution. Yeah, that's what has to happen. Okay, let's keep moving. Here I'll probably substitute for x. That might be easier. You do want to be, you don't always have to substitute for y. You can substitute for x. So y, y will equal y squared minus 2. So 0 equals y squared minus y minus 2. Factor the sucker, y minus 2, y plus 1, y equals 2 or -1. And then solve for x. When x equals 4, there we go. So you have 4 comma 2 as a point. Or x will equal 1. So we have -1, 1 comma -1 also as a point. And again, you're going to have a parabola. Now, this is a sideways parabola. If you're graphing on Desmos, it's actually a sideways parabola. And y equals x minus 2 kind of looks like this. So it looks like you're going to have 2 points in common at x equals 4 and x equals x equals 1. So that makes sense. Again, just punch in the Desmos. You could punch C, the first equation C in the calculator, but the problem is that because y is not isolated, you have to say y equals plus or minus root x. You actually have to do 2 different equations. So much easier if you just type in the way it looks in Desmos. Desmos is way more powerful than the graphing calculator, which probably is why now we're seeing it being used on the SAT instead of just the graphing calculator. It is more powerful because you can just type the equation as it is and you'll see something like this over here. And lastly, you have 2 linear equations back again. 4x minus 2y equals 10, y equals 2x minus 5. And right off the bat, I suspect this is also going to be, actually, I think it's going to be implementing solutions, if I'm not mistaken. Now, A, how did I know that was no solution right off the bat? Because I saw 2 lines with the same slope, but different y-intercepts. Those are 2 lines that don't touch. D, I believe they're going to be the same line. And you could rearrange some things here. What if I rearrange this equation where I move the y to the right side? So I have this. And move the 5 to the left side. So I have this. Now let's stack the equations. The first equation is this. The second equation is this. And basically, the second equation is half of the first equation. In fact, if I multiply the first equation by 2, this is using a process called elimination, which you could do for linear functions, where you try to eliminate a variable by multiplying one or both equations by a constant to make one of the variables look the same. But the problem is that now everything looks the same. And if you subtract, you might be getting 0 minus 0 equals 0. So you get a true statement. 0 does equal 0. All the variables go away. So this means this is these two equations will be true for infinite points. There are infinite points that make this work. For example, I think if I were to plug 2 in for x, or 3 in for x and 1 in for y, that'd make the first equation true. It'd also make the second equation true. Or if I were to plug in, say, 4 in for x and 2 in for y. Is that right? 4, 3, my bad. That also would make the second equation true. So there's infinite points that satisfy both equations. They are the same line. And again, you can go to Desmos and do that really quickly. Just type it like it looks, 4x minus 2y. Come on. Here we go. 4x minus 2y equals 10. And the other one was, I forgot how it looks. Y equals 2x minus 5. Y equals 2x minus 5. Yeah, you see that one line is overlapping the other. So that's infinitely many solutions. And again, the graph confirms algebraic solution because they're intersecting everywhere. So there's infinite solutions, infinite possibilities where they touch. So that's how you want to look at it. So this is infinitely many solutions. Infinitely, nope, don't want to edit the PDF itself. There we go. And we're going to explore this in some great detail. And the College Board, if you're a junior taking SAT sometime early next year, or sophomores will do that, in a year from now or so. They love asking these questions about no solution, infinite solutions. In fact, they like to have you work backwards and kind of deconstruct it. They'll say, hey, here's a system that is no solution, and you don't know some of the constants or some of the coefficients. What will those coefficients be to force that situation to happen? They love those kind of questions. And I'll show that to you guys when I'm back on campus. The ones that are a little bit higher order in critical thinking. Those are great questions. In fact, I love those questions. And might be a test question. So we'll talk about that when I'm back on campus. Okay, let's keep moving here. So here they say the first equation is a circle. Okay, we haven't really talked about equations of circles, but just so you know, the first equation is a circle. Second one's going to be a parabola. We know this. They want you to sketch the two. How many solutions do you expect? And then solve algebraically. So what does the second equation represent? Well, we know that's the second equation is a parabola. We know that. And of course, it opens up. And also it has a y-intercept -13. If you plug in 0 for x, you get -13 for y. Do a quick sketch. Well, they tell you that the first equation is centered at the origin has a radius of 5. You're told that, so just go with it. Let's go blue here for a bit of contrast. And then the other one is simply a parabola. That opens up. There you go. So we could expect 4 solutions because there's 4 points of intersection. Now, I did make this parabola pretty skinny. I'll do a quick sketch again. You don't have to draw the sketch, but who's to say it couldn't have been like that? I mean, there could have been no points of intersection, right? Could have been really wide. So I am kind of guessing here. Like, I don't know how wide the parabola is going to be exactly. So it could be no points of intersection. That's a possibility. Or it could be it could be 2 points of intersection. Maybe it just like grazes it on both left side and right side. Maybe it could be that. I don't know. Let's work it out. But the graph will confirm our algebraic solution after we do the algebraic solution. So we will graph this afterwards. So let's do some solving here. Yep, see, verify by making sure both equations are, well, that's more plugging back in to the equations. But they had x squared plus y squared equals 25. And about y equals x squared minus 13. So guess what? I'm going to do some substitution. Actually, I'll substitute for x squared. It'll be easier. Because then I can replace x squared straight up. Y plus 13 plus y squared equals 25. Move everything to one side here. Y plus 4, y minus 3. Y equals -4 or 3. There we go. Y equals -4 or 3. So if you plug in -4 for y, x squared will be 9. So x is plus or minus 3. If you plug in 3 for y, x will be plus or minus 4. So you can have plus or minus 3 comma negative 4 as an answer, and plus or minus 4 comma 3 as another answer. So that first graph I did, where I had the parabola touching 4 times, seems to make sense. Like, it looks like we have a point at 3, negative 4, a point at negative 3, negative 4, a point at 4, 3, and a point at negative 4, 3. To verify, just plug each point back into the original equations. Just make sure the left side equals the right side. It definitely would for the first one, definitely would for the second one. So we're confirmed. Everything works fine. I don't have to show you that process. I think you trust that, plug those numbers back in. I trust you guys can do that just fine. And make sure the left side equals the right side. So to verify, simply just plug in each solution into each equation and make sure the left side equals the right side. Would I ask you to do that on a test? I won't require it because it does take some time. I think probably maybe we would allow a calculator so you can graph to see for yourself that you do see these solutions. The only problem is that to graph the circle and the calculator is a little tricky because you have to isolate y, and then you'd have to put plus or minus when you square root both sides. So it does become a little tricky to do that. In the interest of time, I won't do that in this video here, but you could isolate y for x squared plus y squared plus 25. It would be y squared equals 25 minus x squared. You'd square roots, but you have to put plus or minus. So it would be positive root 25 minus x squared and negative root 25 minus x squared. You graph the top half and bottom half of the circle, then you graph the parabola. You would see 4 points of intersection on the TI-84 calculator if you had that. Okay, one more page of notes here. How can we just have a different number of solutions? Well, you could actually reduce the circle. you could shrink it, or you could also maybe expand the parabola where it's wider. So you'd have a coefficient in front of x squared that's a fraction to make it wider. So that is possible. What my adjustments can you make? So you could reduce the radius for equation 1 so that the parabola completely misses it. What if you have a super tiny circle and the parabola misses it? Or you could vertically compress equation 2, meaning a is less than 1, where a is the coefficient of x squared, so that you make the parabola wider. So those are some things you could do. Or yet another thing you could do is shift the circle. You could shift the circle to the left or right, so it misses the parabola. So say the parabola does this, and the circle's like over here. That could happen. Or you could put it like down below, so it doesn't touch it. You could also shift the parabola up. That's yet another way. You could have change that to like plus 13 if you wanted to, or you reflect it, right? That could happen. Have it open down instead of up. So a lot of different things you could do. So yeah, did anyone on your team do it differently? Well, sorry, I kind of gave that away because I'm not there to run this as a group situation. This is all individual watching videos. But talk to people at your table, see if anyone may have another idea. Those are 5 ideas I just came up with again. Reduce the radius of the circle or shift the circle left or right. So there's the 2 reasons right there, like reducing or like making the radius smaller or moving the center right? Because that would move the center when you shift the circle left or right or down, or up. No, that's also a possibility. For the parabola, I could shift it up. That's one way, or I could reflect it. That's another way, or I could vertically compress it. That's yet another way. So there's a lot of different things you could do. And what minor adjustments can you make to get just one solution? Again, you could. What I probably would do, actually, the more I think about it, I probably would reflect. Okay, I can't spell. I probably would reflect the parabola and shift up so that the vertex touches just one point on the circle. That's what I would do. So in this case, I could do something like that. So, I could say, and that would be y equals negative x squared minus 5. I could say that because remember the circle had a radius of 5 and had a point at 0, negative 5. So I can do that. That's a possibility. So this is a really great question because it's really kind of forcing to think a little bit outside the box, think a little more critically here about how you can alter the equations to get particular solutions. I said that earlier, like I like those kind of questions, like especially for two lines that have no solution or implementing solutions, what can you do to the equations, or what would the constants be in order to force that situation to happen? And I'll show you some examples of that when I'm back on campus. I think that's pretty much it. What can you do to make have 2 or 3 solutions? I'll just show you graphically how that would look. We don't have to actually come up with some algebraic situations, but you totally could have 3. What if the vertex, what if I have y equals x squared minus 5? So the vertex and a point on the circle touch, and then you have 2 more points. 2 solutions, that's a little hard to think of how that could potentially look, but I know that could happen. Here you have a circle. Yeah, let's think here. You have such a way where they kind of just graze each other like that. That could happen too. And so yes, you can. I just did it for you here. Keep the circle the same and just do y equals x squared minus 5. Just have to think a little hard about it, but that's okay. We don't need to do that for today. Okay, homework is shown down below. And I attached it to the notes that your sub will hand out. So solve each system using any method. So you got right there. So you could just isolate x, do your best to isolate x. I'll share the answer key in a little bit and put it into Schoology. I'll put it next to the homework 27 assignment in Schoology so you can see this answer key. This one here is asking some sort of hypothetical, or not hypothetical. Anyway, this one's a learning log, just kind of reflecting on your learning. 440 is like the first example we just did. So that's a substitution, solving. 441 is more solving again, just solving, isolating the variable. 445 is domain range, old stuff there. And extra practice if you want it, it's right here. Okay, I think we're all squared away. All right, well, enjoy the rest of the day. And I won't be on campus tomorrow morning either. Actually, I'll be on campus in the afternoon for a meeting. So I won't be there for office hours today or tomorrow, but definitely on Wednesday, I'll be there for office hours, and I'll be there all day Wednesday, Thursday, and then Friday, just for if you're a D period for our morning classes. And I'll be leaving campus early to start Thanksgiving break after Friday. So, but anyway, definitely I'll see you guys on Wednesday. So, yeah, because I'm not going to be on campus till much later tomorrow for a meeting. All right, I will see you guys later. Goodbye.